In this series of lectures, we introduce some basic and important concepts in calculus. As an entry-level course, we often adopt approaches that are intuitively clear, but might not be mathematically rigorous. In particular, we will not use the famous epsilon delta language. In this lecture, we'll look at the important fundamental theorem of calculus. This provides an efficient way to compute the Riemann integrals of many functions. Okay. First, let's look at part one, the Newton-Leibniz formula. As we know, the calculus was independently introduced or invented by Newton and Leibniz. Here's the setup. Suppose we have a function f, which is continuous on the interval AB and differentiable on the open interval. Then we can talk about the derivative function, the Poincare. Let's assume this derivative function is Riemann integrable. For example, it's continuous or piecewise continuous. Okay, so continuous and piecewise continuous are probably the most often used special examples of integrable Riemann integrable functions. All right, if that's the case, then we have the integral of the derivative function equals the difference of the value of f on two endpoints. This is the Newton-Leibniz formula. Because this formula is extremely important, let's prove it. Okay, so first of all, let's recall how we define the Riemann integral. We use the Riemann sum, right? We divide the interval into small pieces, and then we send to the limit. That means we divide in final and a final way. Okay, so let's say this is A and this is B, and we divide into n pieces. Right? First, let's say n pieces. So this is x0. Right? So this is x1. This is x2. This is x3. Right? This is x4, and such. Okay, let's say this is xn. Right? So this is xn minus 1. Right? In the middle, this is xi minus 1, and this is xi. Okay, so we divide it into n pieces. Okay, now let's write the fa minus fb. We are going to insert those values x1 up to xn minus 1 into the difference. Okay, so here we have this fb minus fa. Okay, let's look at that. Write fb minus fa equals, now I insert those values, so it's fb minus the one before it, which is xn minus 1, right? So it's hn minus 1. And then we plot this one back. This is xn minus 1 and minus xn minus 2, right? And then you plot f xn minus 2 and then minus f xn minus 3, right? Okay, and such. The last term will be here. This is the f x1 fx1, right? Minus fa. So this is the last term. And that's middle term, maybe the middle I write. Let me write one more term. So in the middle, okay. In middle we have, so okay, this is f, this is x I minus fi minus 1, and then the last one will be f. This is x1 minus fa. Okay, you see the left-hand side and the right-hand side are the same because all those terms in the middle, they cancel with each other. So this one cancel with this, right? And this cancel with this, right? So the point is all the middle terms, they just cancel with each other, and the left-hand side and the right side are the same. Now, what's next? Next, we are going to use the mean value theorem to connect the function f with its derivative. Okay, so let's recall the mean value theorem. Here we have this mean value theorem. Mean value theorem says this. Okay, let's use this one as an example, right? So fb minus fxn minus 1, right? fb minus fxn minus 1. We are going to link this to the derivative of f, right? Let's recall what the mean value theorem says. So here is, right, so let's say we only focus on the piece. Let's say this is x, this is y, right? Here I say this is x n minus 1, and this is the b. Okay, so we have the graph. Let's say the graph of the function between this interval is like what I draw here. So this is fx, right? Okay, now the mean value theorem says this: if I connect the two endpoints, right, and then of course I have a slope k, right? So this slope k equals f, right? So f b minus f x n minus 1 and divided by b minus x n 1, right? So this is the slope. Geometrically, if you parallel move the line, let's say move up, right? So here's move up, then at some point it will touch it, right? It will touch it. Okay, so I say this, I can write at this x n star. So, okay, it will touch the graph at the point, at one point, and then because they're parallel, and the derivative at this point will equal to this slope, right? Equal to this slope. The two things are the same. This is the mean value theorem, right? What it says. Right? You can find the point between two endpoints such that the derivative at the point equals the slope of the line connecting two endpoints. Okay, so from here, you see, okay, if I rewrite this one, I will just get the fb minus fn minus 1 equals the derivative of f evaluated at some intermediate point and times b x n minus 1. Now, of course, we can extend this to any interval, say xn and minus xn minus 1, right? So the same. So we just apply the mean value theorem. Okay, then if I write this, in general, this one can be write as, it's okay, I can find a point in the middle, so derivative xi star, right? So this is some point, so this is xi minus 1, this is xi, this is somewhere between, and times xi minus xi minus 1, right? Okay, now then you say, okay, we can write as a summation. So the whole thing can write as summation, right? This I from 1 to n and f prime evaluate at the intermediate point and times the difference of xi minus 1. And then you look at this, you say, what is this guy, right? What is this guy? You find this is a Riemann sum. This is a Riemann sum corresponding to this partition, right? Corresponding to this particular partition. And you have the sample points, which is from the mean value theorem. Now, of course, the Riemann sum in general depends on how you divide the domain, right? How you divide the interval, how you choose the sample points. Okay, but here what we have is that the same, right? We say okay, they're the same. The function is Riemann integrable, just means, okay, by the assumption it's Riemann integrable, just means regardless how you divide the interval, regardless how you choose the sample point. This limit, if I send the limit, if I let the division as final, which means this one will go to 0, right? So difference goes 0. Of course, then you'll get the number of pieces, or will go to infinity, right? If you do that, right? If you divide more and more into more and more pieces, eventually it will converge, right? It will come. The limit will equal to this. This limit will equal to the Riemann integral, right? Will equal to the Riemann integral from a to b and L prime x and dx. This is how we define, right? So this is how we define the Riemann integral. And then you see on the left-hand side, it never changes. It's always fb minus fa. Okay, so if you send limit on both sides, if you send the limit, you see the left-hand side never changes, and the right-hand side, it goes to the right-hand side, it goes to the limit goes to the Riemann integral. So we establish this Newton-Leibniz formula. If you review the proof, what do we use? So first of all, we did a simple algebraic factor, which is intermediate. We just insert those intermediate points, and then we apply the mean value theorem. Now, the mean value theorem basically links the derivative with the difference, right? With the difference between the value of endpoints. So mean value theorem can be viewed as some kind of discrete version of the Newton-Raphson formula. Okay, so then if you put everything into here, what we basically get is a special Riemann sum. And because the derivative is integrable, so if you make the division as finer, and then the limit will go to the Riemann integral, right? And because the left-hand side never changed, so this gives us the Newton-Raphson formula. Now, by the Newton-Raphson formula, you say, okay, suppose, right, you want to compute the Riemann integral of a function fx. And then what you should do? Well, what you need to do is you need to find the function so that its derivative equals fx, right? So you need to find at least one of them, just find one of them. If you say you successfully find one, then you will just get, okay, if I find one, then by the Newton-Raphson formula, the first part of the fundamental theorem calculus, you say, okay, so this will just equals fb minus fa, right? Okay, so the point is, so in order to solve a Riemann integral, the key is, if you want to find the exact value, the key is you need to find a function so that its derivative equals fx. So by the way, when you look at, when you compare the derivative with integration, you can kind of say that the derivative, the integral is basically inverse of the derivative. All right, so you need to find this. Now, such kind of function is called an antiderivative of fx. So if the derivative of capital Fx equals the lowercase fx, then this one is called the antiderivative of f. All right, and then in mathematics, we can express, we say the antiderivative of this equals the capital Fx plus a constant c. You say, hey, why do you want to add a constant c? That's because if we have the f prime, this one equals to f, right? Then you add any constant, whatever it is, right? So the derivative, which is the derivative of f plus the derivative of constant. But the derivative of constant is always 0. So the point is, if you add a constant, does not change the derivative. So it's still fx. All right, this gives us the general expression of the collection of all the antiderivatives of a given function x. So that's why we need add a constant, whatever constant it is, right? Okay, all right. Let's look at some examples of antiderivatives. First of all, let's look at if we have a power function x to the power a. So a is the power which is not equals to -1. Then this is its antiderivative. You say why? That's because you see, if I take the derivative, right? If I take the derivative of this, according to power function, so this will be I f plus 1 and x to the power alpha. So if you divide by this, you cancel, you get is xi, right? Special cases, again, don't forget, you just add a constant because adding constant is not going to change the derivative of a function. For example, you see, okay, what do we have? You see, if we have, you say, okay, if I have the, what is the antiderivative of this? Because power is 1, right? So here's power is 1, it will be just x squared over 1 plus 1 is 2 and plus a constant, right? And then you say, okay, how about of x squared dx? This will be 2 plus 1 and x to the 2 plus 1 and plus constant. So it will be x3 over 3, x to the power 3 and plus c, right? And then you say, okay, how about the square root of x dx? And of course, we assume x is positive. Now, this is just x to the power 1/2. So what we have is 1/2 plus 1 and x to the power 1/2 plus 1 and a plus constant. And you write this, okay, so this is 3 over 2, and you flip it, so it's 2 over 3, and x to the power 3 over 2, and a plus the constant, plus a constant, right? All right, so this provides the general formula to find antiderivative of the power function. And then what if it's a negative one, right? So this is the power case, is negative one, right? For this case, because we know the log x to the derivative is 1 of x, right? So if you find the antiderivative, then of course the antiderivative of this, which is the log x, right? Okay. So remember, we have to remind ourselves. Okay, so this one equals capital Fx. This just means by definition, just means the derivative on the right hand side equals this little fx, right? Little fx. Okay, so next one, the antiderivative of 1 plus 1 over 1 plus x squared is arctangent. That's just because we know the derivative of arctangent x, this is 1 over x squared, right? Okay, let's look at more. The antiderivative of sine x is negative cosine x. That's because we know cosine x, the derivative is negative sine x. So negative cosine x derivative will be sine x. So that's why the antiderivative of sine x is negative cosine x. And here is similar because we know the derivative of sine x, there's no negative sign, so it's cosine x, right? And here, okay, one find derivative of e lambda x, right? If for lambda equal 1, we know ex, the derivative of ex just ex self. So the antiderivative of ex is just ex plus constant. Now, if you have parameter lambda here, right? If you have for parameter lambda, we know lambda x, if you take the derivative by chain rule, right? Apply the chain rule, you can see this as y, right? So this is, okay, let's say this is, you can see y. If you apply the chain rule, you will see this equal to e lambda x. And you have to multiply it by lambda because when I take the derivative lambda x, you get lambda. Okay, so by the chain rule, right? Okay, so then if you divide by lambda, if you divide by lambda on both sides, you get rid of the lambda. Okay, so that's the antiderivative of e lambda x. And this one is similar, just because you recall if a is positive, what's the derivative of this exponential function when the base is a? In general, we know it's a to the x and the log x. It's the log a, right? It's the log a. Okay, so if you divide log a on both sides, right, then you get the derivative of ax over log a equals ax, right? So that's why you get this antiderivative. Now, if you add an extra lambda, then apply the chain rule, it's the same thing, right? Okay. All right, so the point is we just recall those derivative functions we found in the past, and then we just connect the derivative function with the original function, right? Okay, and then this will give us those antiderivatives just by memories, right? Okay, now let's review how we compute the integral of this function from 0 to 1 x and dx. Okay, we can have two methods now. Method one is the method we used before. We say, okay, we forget about the Newton-Raphson formula. Let's just use the geometric meaning of integration. So this is what we did in the previous lecture. Geometric meaning. Okay, it's the area. It's okay. Let's look at this is the graph, right? So this is the graph, which is from 0 to 1, and this is x, and this is y, 1. Here's the graph is y equals to x. Okay, this is the graph of y equals to x, and this integral represents, because it's positive, right? We think here the function is non-negative. It represents the area of the region that's below the graph above the x-axis. Okay, so it's the area equals the integration from 0 to 1 and x dx. Because this is a simple region, it's a triangle, and we did before, the area just equals to 1/2, right? So without using any advanced theorem and just by the geometric meaning we get this, it's okay, this one equals to 1/2. Now, let's check this using the Newton-Raphson formula and to see whether it matches, right? Method two, let's use this Newton-Leibniz formula, which is part one of the fundamental calculus. If you look at different versions, sometimes this is Newton-Leibniz formula is listed as the part 2, but it doesn't really matter. Here we just change the order. Okay, if we use the method 2, then we say, okay, the antiderivative of x is the x, right? And this one, where we know it's just x squared over 2 and a plus constant. So this will be my fx, right? And then the integration of this and x dx, we know, okay, so this just equals to the f1 minus f0. Very often we write this as x squared over 2 and e-value at the endpoint. So this is just a common way to write, to represent the difference of these two. Okay, so then we just get it's 1 square minus 0 square over 2. And again, we get is 1/2. So they match. All right, now let's look at an example. Here we want to find the area. Okay, so here we want to find we have a function which is sine function. Okay, so this is x and this is y. Okay, sine functions. This is the sine function. Okay. It's from 0 to pi. We want to find the area of the region below the graph y equals sine x. This is y equals sine x, and above the axis for x between 0 and pi. All right, so it's right here. So we find the area of this region. Now, as we mentioned in the previous lecture, if we call the geometric meaning of the integral, right? If of the integral, this is the area below the graph, right? Area below the graph. If it's positive, right? If it's positive, if this is, let's say it's positive function. Here, from 0 to pi, the function sine x is positive. So we say this area, okay, all right. So the area just equals the integration from 0 to pi, right? And sine x and dx, right? Sine x dx. Now, because we know the antiderivative of sine x, this just equals to negative cosine x, right? So this is fx. Okay, so by the Newton-Leibniz formula, so we apply the Newton Leibniz formula. Leibniz formula. Okay, so this will equals to this f pi minus f0, right? F0, right? Sometimes we write this is cosine x, right? So this is cosine x because fx cosine evaluated from 0 to pi, right? And 0 pi. Okay, so it's negative cosine pi minus, right? Negative cosine pi minus negative cosine 0. Okay, what do we get? Negative cosine pi is, okay, cosine pi is -1. Cosine 0 is 1, right? Okay, so then this one is equals to 1. And this is -1, but negative for -1, you get is +1. So the answer is, final answer is 2. So 2 is the area below the graph of sine x between 0 and pi. Next, let's look at past problem from AP calculus, AP exam. What do we want to look at? Let's look at this. Okay. Again, we want to find the area, right? This is the x, this is y, and this is 0. We want to look what's the area of the region enclosed by the graph of y equals 0. Now, y equals 0 is just the x-axis, right? So this is the x-axis, y equals 0. And then y equals to x over 1, and x equals to 1. Okay, x equal to 1, let's put it here. So this is x equal to 1. Let's put this is 1. This is the line, put it here. This is x equal to 1, and some point c, which is between 0 and 1. Let's say it's right here. Okay, so let's see, this is the c, right? This is the line, which is x equals c, and then y equals to x1. Now, then we know this point pass through. If x is 1, y is also 1, right? Okay, so this pass through this point and the graph, and we look at the graph. See, it's so this is the part of the graph, right? So, okay, so that's the part of the graph. This is the part of the graph we're looking for. It's y equals 1 over x, right? Okay, what is the region we're looking for? We are looking for is this one. It's bounded by y equals 0, x equals 1, x equals to c, and below the graph, y equals to 1 over x. Okay, so now we know this is just the area, right? So we have the area is just equal the integral, right? Just integral from c to 1, so from c to 1 and 1 over x and dx. Right? So this is the geometric meaning of the Riemann integral. And okay, well, this one is just equals to, the antiderivative of this is just the log x, right, plus constant. And then, okay, so you can choose this, just the capital Fx. Okay, so there's just the capital F1 minus Fc, or you can just write as the log x evaluated on endpoints into the difference. Okay, so that's what you have. This is log 1 minus log c. What is log 1? Log 1 equals 0. So what you have is negative log c. Okay, so the area is negative log c. Okay, little c, and that is the area, the answer, negative log c. Okay. All right, let's look at next example. Suppose a particle is moves along the x-axis. Okay, here we have particle moves along the x-axis, and the velocity, which is the instantaneous velocity, at time t is 6t minus dt. Okay, so we have the velocity function is 6t minus t squared. In particular, it's not constant, so it changes. So that's why I call it instantaneous speed. The question is, what is the total distance traveled by the particle from time? Let's say this is the time t equals 0 and to the point t equals 3, the travel distance, right, from here. Okay. All right. Okay. Whatever. So that's just how we mark it. Well, you see, we want to find is the total travel distance, right? Total travel distance, total distance, and this requires to recall the physical meaning, which is one of the most important applications of integral in physics. Okay, let's recall the physical meaning. Right, if I take the integral of AB of the velocity function, and this is the travel distance. Right, so between two time A and B. Okay, so all we need to do is we say, all right, this just requires us to find the distance, the total distance by the particle, which just equals the integration, right, from time 0 to times 3 and 6t minus t squared and dt. Now, because the integration is linear, we can just separate this as from 0 to 3 and 6t dt minus from 0 to 3 and this t squared and the dt, right? And then we can just calculate them separately, right? Let's look at this. On a calculator from 0 to 3, 6t dt, and 6 you can move to the front. So this is 6 from 0 to 3 and t dt. We know the antiderivative of t, this is t squared over 2, right? We said before, plus constant. Okay, and this will be my capital Fx, which is this an antiderivative function. Okay, so then this will be just 6 t squared over 2 evaluate, take the difference of two endpoints, right? So this is how we write it, which is, so this, okay, so F3 minus F0, right? Of course, don't forget the 6. Okay, so then we get a 6, this will be a 9 over 2. It will be 9 over 2. Let's see, make sure everything is correct. Right, yes, I think so. So, okay, so then you get is this 3. So, okay, we can get a 27. So for the first guy, so this will be 27. Now let's calculate the next one, right? So let's calculate this one. Okay, so we have the integral from 0 to 3 t squared dt. Let's recall the antiderivative of this one is t3 over 3 and plus constant, which is this will be my fx. Okay, so then this one will be just f3 minus f0, or we say, okay, we write t cubed over 3, evaluate at 10 points and take a difference. Okay, so then you get, this is what you have, and then you get is, will just be 3 to the 23, which will be 9, right? Which will be 9. Okay, so then we get this part is 9, and eventually the distance will just be 27 minus 9, which is 18, Okay, so this is what we have. All right, so I think everything is correct. Okay, now let's look at another question from the past AP Calculus AP exam. Here, what we want to find is the antiderivative. Now, antiderivative is integral form. We know this. You can separate this just like it's linear. Right? Okay, just like the integral itself is linear. We can separate this, the antiderivative of 1 over x and dx. This one we know, right? So this one we know. This one is just the log x. Of course, you just plus whatever constant, right? Okay, so this is log x, and then you say, hey, how about this one, right? So how about this one? This one you can use the formula. This is just remember. Let's recall the formula. If it's the a to the lambda x dx, what's the antiderivative? The antiderivative equals 1 over lambda log a and a to the lambda x, right? Here the lambda is 2, so this is the 2. Okay, so then if you remember this formula, you can just quickly get it. You say, okay, so this is just 1 over 2 log 5, right? So this 2 log 5 and times 5 to the 2x and plus this log plus c. Okay, so eventually the answer will be 1 over 2 log 5 to the power 2x and plus log x plus a constant c. And you can double check. You see, okay, if you can double check, if you take the derivative of this each term, you get this is 2x plus 1 over x. Okay. Let's look at example 5. Here we want to look at the integral of the function. What we can do is we can separate this into 2, right? Okay, so let's see. This is from 1 to 2, t plus 1 over the square t and dx. This can be written as from, let's see, so t plus 1 over the square 2t, right? T. I can write this as t over the square t plus 1 over the square t. So t over the square t is square t and plus 1 over square t, right? Okay, so this is just from 0 to 2, square t plus 1 over square t and dt. We can because remaining integral is linear. We can write into 2 terms. The integral of sum equals sum of integrals. Okay, so this is from 1 to 2, square t and dt, and plus from 1 to 2, 1 over square t and dt. And then remember, then we just apply the antiderivative, right? Let's recall. If I recall the antiderivative of square 2 dt, this is what we did before. This should be 2 over 3 t to the power 3 over 2 and plus some constant, right? Apply the formula. How about 1 over the square t dt? Let's write this guy as power, right? So with the power. So this is t to the negative 1/2. Okay, so if we apply the formula, we'll just get this is okay. So this will be t negative 1/2 plus 1 over 1 plus negative 1/2 plus constant c. And then what you get is just twice the square root of t, right? So this one is just equals to 1/2, right? Okay, square t and plus the constant c, right? Okay, so then we can just use, so this will be the fx for the square t, and this will be the fx for 1 over square t. All right, and then we just put this into here. We got a 2 over 3 t to the 3 over 2. You evaluate at endpoints, and the plus twice of square t, you evaluate at endpoints. Okay, and let's plug into. Okay, what do we get? Eventually, we get a 2 over 3, 2 over 3 over 2, and then you minus 1, right? And minus 1, and then plus 2 times the square root 2, and minus 1. Right? You can combine the things together to the form you like, right? So it's 2, and this is 2 to the 3 over 2, and minus 2 over 3, and then you see 2 times square root 2. This is 2 to the 3 over 2, right? 2 to the 3 over 2, and then it's 2 to the 3 over 2 and minus 2. Okay, so you can combine everything, and you'll get these two things you can combine together, right? So then you get 5 over 3 times 2 to the 3 over 2, and minus, and then you combine these two things, will be 3, 8. This is the final answer we get. Okay, all right. Example 6. Let's find the integration of the absolute value of x minus 1. Now we don't have obvious antiderivative of the absolute value. So what we can do is method 1 you can use geometry, because you say, oh, this is kind of like simple function. So maybe we can use geometric way to do it, right? So method 1, we just use the geometric meaning. Let's use the geometric interpretation of integral, which is area, right? Okay, so then what we do is let's draw the graph of the function. I draw the graph. Y equals, so okay, we're looking at y equals the absolute value of x minus 1. So this is x, and this is y. We start from 0 and to 3. This is 0.1. Okay, if it's the yx minus 1, and you see the graph look like this. So this will be the graph. Okay, you're here, and then you go up to it. Yes, 2. All right. This is the graph. This is the graph. This is the graph of y equals the absolute value of x minus 1, right? Now, you just want to find the areas. Okay, so the integration is just equal the area. Integration from 3, x minus 1, and dx is just equal the area. Now, area has 2 parts, right? We have 2 parts. The part of this, which is 1/2, it's a right triangle with length 1/2. And the part of this will be 1/2. You see times here it will be 2, and this is 2, so times 2 times 2, and this will be 2. So part of this will be 2. Okay, so if you add them together, it's 1/2 plus 2 will be 5 over 2. Right? Okay, so the point is you can use for this simple function, you say, okay, I can just use the geometric meaning without using the Newton-Raphson formula. All right, let's see if we use Newton-Raphson formula, how we do it, right? If we encounter things with absolute value. So how should we do it? So method 2, we use the general formula, so Newton-Raphson formula. Okay, to use the Newton-Raphson formula, we need to let's get rid of the absolute value sign. Okay, so we know this one equals it's 1 minus x if x is less or equal to 1, right? And it will be x minus 1 if the x is greater than 1 or greater equal to 1. It's a continuous function. Okay, so then when I do the integration, I can do separately. So I say I go from 0 to 1. X minus 1 dx, right? And then we integrate from the second part, which is from 1, which is greater than 1, right? So 1 to 3, and this is x minus 1 and dx. Okay, and then because of we know the sign of the x minus 1 in these 2 intervals, that we can get rid of the absolute value sign. Okay, so then you see this is the first part with 1 is 1 minus x and dx. And the second part will be from 1 to 3, and this will be x minus 1 dx. Okay, now my point is if we encounter things with absolute value, so what you should do is we should get rid of the absolute value sign, right? Okay, right. Let's say we don't care about what is the antiderivative of the absolute value. Just for convenience, we get rid of the absolute value sign. Okay, then let's see what we get. For this one, we say, okay, so this is from 0 to 1 dx, right? And minus from 0 to 1 and x dx. And this part will equals from 1 to 3 and x dx minus from 1 to 3 and 1 dx, right? Okay, so this part will just be 1 because it's constant and the length is 1, so it's 1. And this will be x squared over 2 and evaluate at endpoints, right? And then plus this is x squared over 2, you evaluate endpoints, and then this will be 1 times the length 3 minus 1, so which will be 2. Now, if you combine all those things together, what we get? We say, okay, so this will be 1 minus, this will be 1/2, right? So this will be 1/2, And then you plus, this will be a 9 over 2 and minus 1 over 2, right? And then you minus 1, subtract 1. So what do we get? It's 1 minus 1/2, and this will plus 4 and minus 2, right? Okay, eventually we just get so this is the 5 minus 2, so it's 3 minus 1/2, right? So minus 1/2. So eventually you get is 5 over 2. Let's check. Okay, so you see it's the same. It matches what we got from this geometric meaning. So it's 5 over 2. Right. Okay, all right. Now let's look at example 7. Here we want to do the integration from 2 to 3, 1 over x squared minus 1 and dx. Okay, here again, we try not to just find the antiderivative 1 over x squared minus 1 directly. Let's try to simplify it, right? Of course, we can do the antiderivative thing, but let's try to simplify this one first, or write in the way that we like it. Okay. What we can do is we can use the those partial fraction decomposition. Okay, so this one we know is 1 over 1 x minus 1 and x plus 1, right? Okay, so then by a partial fraction decomposition, we can get this is just 1/2 and 1 over x minus 1 minus 1 over x plus 1. Now we like those things because you see they're just basically log, the antiderivative just log function, right? You just shift the plus minus 1. Okay, so then what I get is, okay, if we try to get the integration from 2 to 3, 1 over x squared minus 1 dx, you say, okay, so this is 1/2, right? The integration from 2 to 3, 1 over x minus 1 minus 1 over x plus 1 and dx. Now, because the integral is linear, so we can write it out. So here is the integral of the difference equals the difference of integrals, right? So, okay, so this dx minus from 2 to 3 and 1 over x plus 1. This is dx, right? Okay, now let's calculate this. What is the antiderivative of x minus 1 dx? Well, remember the antiderivative of this is the log x, right, plus constant. Here is you change it from x to x minus 1. So expect we say, okay, by chain rule, there just should be x minus 1 and plus constant, right? Plus constant. Again, so here we assume x is, for convenience, let's assume we look at x is greater than 1, right? You can check because by the chain rule, the log x minus 1, if you take the difference, take a derivative, it's just 1 over x minus 1. Again, we look at x greater than 1 case. Okay. And then similarly, you get the antiderivative of 1 over x plus 1 dx. This is just the log x plus 1 and plus the constant c. Okay, so from here, then you get this is 1/2 the log x minus 1 evaluated at endpoints, right, minus, and this will be log x plus 1 and evaluated at endpoints, right, endpoints. Okay, then you see what we get. We get this is equals to 1/2, right? And here will be log 2 minus log 1, and then minus, this will be log 4, log 4 minus log 3, right? Log 4 minus log 3. Okay, log 1 is just equal to 0. If we combine all of them together, we get a 1/2. Here will be log 2 plus log 3 and minus log 4. But you see, 4, we can further simplify this. So this 4, we know is just 2 to the square, right? 2 to the square. To the square, okay? So then this just equals 2 times log 2. Okay, log 2, they cancel 1. So you get this log 3 minus log 2, right? So eventually you just get the answer is 1/2 and log 3 minus log 2. And this you can further simplify it. If you remember from high school, the law, so this is log 3 over 2. So the final answer is 1/2 log 3 over 2. Okay, by this computation, we actually also derive the antiderivative, right? If you look at, say, okay, the antiderivative of 1 over x squared minus 1 dx, let's assume the x is bigger than 1, right? So antiderivative, we say, okay, this is the antiderivative, 1/2. This is 1 minus x and minus 1 plus x and dx, right? So you just get this 1/2. This is the log x minus 1 and minus the log, right? It's minus log x plus 1, okay, and plus the constant, right? And then we use the log thing, right? So, okay, use the log thing. So it's a log minus log, so it gets log x minus 1 over x plus 1 and plus constant, right? Again, so here we use several properties of the log function. So log a, all right, plus log b. So this is just log a times b, right? So log a minus log b is just log a over b. Example 8. Here we have a piecewise defined function, which is fx. Okay, let's look at the definition of fx, right? Fx equals x. We have 0, this is 1, and this 2. It equals x when it's between 0 and 1, right? This is 1, this is x, this is y. And then when it's between 1 and 2, it's given by the cubic function. It's the cubic function. So from 0 to 2, it's the cubic function. Right? This is my y equals to fx. This piece is y equals to x. This piece is y equals to x cubed. Okay. It's a piecewise defined function. Now I want to do the integration from 0 to 2. As a property of integral, we can do it separately. So, okay, we first do from 0 to 1 and fx dx, and then we from 1 to 2 and fx dx, right? Because we know in each piece the definition of fx. So this is just x dx, and this is going from 1 to 2, and here's x cubed and dx, right? And then we say, okay, so let's apply the antiderivative. So antiderivative, again, this guy equals x squared over 2 plus c, the antiderivative x3, and this will be known as x to the 4th, the 4, and plus constant c, right? Okay, so it's over 2, evaluate 0, 1. Okay, so then for the second part, because antiderivative of x cubed is x4 over 4. Okay, so this will be x4 over 4 and evaluate at 2 endpoints, 1 and 2, and take the difference. Okay, so then let's see what we get. And then from here, we should get is, okay, so this part will just go to 1 over 2 and minus 1 over 0, because you evaluate at 2 endpoints, take the difference. And then the other part will be 2 to the 4 over 4 and minus 1 to the 4 over 4. Okay, let's see what we get. And here we just get 1/2, and then plus this is 16, so this is 4, and minus 1 over 4, right? Minus 1 over 4. Okay, so the final answer will be 4 minus 1 over 4, right? So it's 3 3/4. All right, so this is the final answer of the integral. Okay, so 3 3/4. Okay, so this one will be 3 3/4. Let's look at example 9. Here we are looking for the limit of 1 to the 4, 3 to the 4, and n to the 4, and over this n power to 5, and m is part of integer, and it goes to infinity. So here the idea is, you see here you have a sum, right? So what's the idea is, okay, try to write 8 into a Riemann sum. Because when you look at this, okay, this is kind of like a Riemann sum, right? So if you have 2 to the 4 and plus 3 to the 4 and n to the 4 over n to the 5, you see, we can write this as the summation. Okay, so if I can pull one n out, and the remaining part will just n to the 4, 1 plus 2 to the 4, 3 to the 4, and all the way to n to the 4. Okay, so then this is just 1 over n, and here's 1 over n to the power 4, plus 2 to the n to the power 4, 3n to the power 4, and the last one is n to the n to the power 4. Okay, if I rewrite this, you see, I can write it as the summation. This is the summation 1 over n, right? Okay. I can write this is the summation. This is I from 1 to n, I over n to the power 4 times 1 over n. And this is a Riemann sum. Say, okay, say why this is Riemann sum? Because if I write this interval, this is interval 0, 1, and I divide into n pieces evenly, so n equal pieces, and then you see the first one will just be 1 over n, this one will be 2 over n, this will be 3 over n, this will be 4 over n, and the last one will be n over n, right? If I divide into n equal pieces. And this is the Riemann sum. And then you correspond, you say the function right here, if I look at the function fx equals 1 over x2, if I look at the function as x to the power x to the 4, right? If I look at the 4, and then you see this is exactly, if I look at use that, this is exactly the Riemann sum. I from 1 to n, f evaluated at I of n and times 1 over n. And 1 over n, of course, is just the step size is 1 over n, and step size 1 over n. Okay, you see, and this is a Riemann sum. Now, if you set the limit, now here what you want to do, you say, okay, I want to set the limit, right? I set the limit go to infinity. I want to set the limit go to infinity. If you set the limit equal to infinity, you see you just get more and more equal pieces, and the step size goes to 0, right? So the step size goes 0. And then this is continuous function. We know eventually it should converge to the integration from 0 to 1 and x4 and the x. So that's by the definition of a Riemann integral. And of course, we know how to calculate this. The antiderivative of the function of this will just be x5 or 5, right? So this plus constant, and this will be x5 or 5 evaluated at 2 endpoints, and it will be 1 over 5. Okay. All right. Next, let's look at the second part 2 of the fundamental theorem of the fundamental theorem of calculus, fundamental theorem of calculus, okay. FTC, fundamental theorem calculus. The part 2 says this: suppose f is a continuous function defined on AB, and then I define a function fx, that is, I choose x between AB, and I do the integration. Right, from a to x. That's the integration from a to f, the function fs, right? Okay, to the integration. Then this, of course, this becomes a function of x. Now the claim is, if you take the derivative of fx, you just get the little x. So in other words, this just implies this is an antiderivative of fx, right? Again, this is a further demonstration that the integration is an inverse function or inverse operation, right? Inverse operation of differentiation. So if you take then the integration and you take the derivative, right, you just get, you see, if I can just rewrite this, I can write as, okay, if you look at the integration of a function and you take the derivative and you just get the function itself. All right, so in this sense, we can say the integration, right? So the integration is inverse operation of the derivative. It goes back to itself. You first do integration, then you take the derivative. It goes back to the function itself. So it's inverse operation. Okay, let's prove this. Okay, so how we do this? Let's say we have this f prime x, right? Okay, so we want to calculate the derivative, right? Okay, let's try to understand this from 2 ways. Okay, so let's say method one. Method one, let's say assume. Okay, so this is not the general way to establish the thing apart, but let's say assume the fx has an antiderivative. Right? That means we can find the gx. There is a gx such that the derivative of gx is just equals to fx. Suppose you are able to find antiderivative. Of course, you might be wondering, how do you know it has antiderivative? Let's say it has antiderivative, right? And then if that's given the assumption, so we say, okay, we'll get the fx equals the integration from a to x, right? And then I can just replace by the derivative. So this, okay, this g prime as ds. Now we can apply the Newton-Leibniz formula by this Newton-Leibniz formula, Newton-Leibniz formula. Okay, and then we say, okay, so this is just gx minus a constant ga. Okay, so we say, all right, from here, I derive this fx, right? So this fx will equals, so this fx will equals the gx minus ga, which is constant. Fx gx minus ga. Then if you take the derivative from here, so okay, let's take the derivative. The gx minus ga, take the derivative. Now this is constant. You take the derivative, which is 0. So again, it's just the same as the gx. Right? If you add count does not change, the derivative you get is fx. So this is a quicker way to see why this is correct using the Newton-Leibniz formula. But here, the problem is we need to assume that f has antiderivative. Okay, but in general, you don't really know, right? Of course, the answer is yes, but we don't really know at this point. Okay, but so this is not the most general way. This is not general way to prove the theorem. Now let me show you the second method, which is the general way to prove the theorem. Okay, so let's look at the second method, which is the usual way to establish this one. Okay, all right. Method 2. This is the general one. All right, let's just apply the definition, right? So, okay, here we have the derivative of this. So I just apply the definition. So let's recall how we define derivative. Derivative by definition, the analytic definition is we say, okay, if I have h goes to 0, right? This is fx plus h minus fx and over h. Okay. Now I plug into the definition. I plug into the definition of fx, and I see, okay, what is fx plus h? F plus h will be from a to the x plus h, right? So fs and ds, right? So you do the integration from x to x plus h, right? So you do the integration from here to here. And then fx is this. So if you take the difference of the two, right? So if you take the difference of x plus h minus fx, and then you just get the integration of this part, right? We say, okay, so then I just get, this is the limit as h goes 0. What you left is this remaining part. So it's x to x plus h. Let's assume that h is a positive. You can look at h is negative, which is similar, but let's say h is positive. Here, that is the fs and ds. Now, here, and then let's look at the integration of x to x plus h, fs and ds. Okay, so this is now we look at within here, within this interval, small interval. Now we use a mean value theorem for integral. It says this. Okay, by the mean value theorem says if you look at the integration, if you take the average of this, right, take the average of this, and this will be equal to, by this mean value integral, this will equal to f evaluate at some point, right? So this is some point, say it's I put a c star, right? C star is some point between here. So this is some point c star equals to that, if to the average. So this is the mean value theorem for integral. It says, all right, so suppose you take the integration, you have function fx that's defined on closed interval AB. Then if you look at the average of fx over AB, it's equal to the value of f for some point. All right, okay. All right, so that's what we have. And then let's see what we get. Then from here, if I apply this, it's okay. So this one will just equal the limit, right? H goes 0, and this H, and H times FC star. And then you just get a cancellation. You still get a cancellation. It's okay. I just get it's the limit, H goes 0, FC star. But let's recall what's C star. C star is something between. So this is C star is something between x and x plus h. So if h equals 0, just means this one will shrink to x. Then of course this will force this star also goes to x. Obviously we get this one. The final answer will be fx. So we start from the definition of L prime x, and we look at use the property of integral, right? Take the difference of integral. So it's the Riemann interval. And then we apply the mean value theorem for integrals. So it's okay. So the average of function of f, right, is equal to some point, the value of f between some point, and then get the limit. It's 2, right? Okay. So this is a general proof. Does not require that f has the anti-derivative. All right. Now let's look at the mean value theorem for integral. Let's see why it's correct, right? Okay. Let's see. Okay, so suppose our function, right? So suppose our function, which is defined from A to B. Okay? This is A and this is B, and here is my function. So this is my function from A to B. Y equals to fx. This is x, this is 0, and this is y. Okay, let's first try to understand this by intuitive argument and see why this is correct, right? Okay. Well, you can think of this as a pi over sand. So you can think of here, the shape of fx gives us a pi of sand. Right? And then you say, okay, I try to smooth it, right? I use hand to level it out. So if you try to level it out, what do you get? You say, okay, clearly, this is the highest spot, right? You try to identify this is the highest spot. Okay? That's the maximum value, the max. And then you have the lowest spot, which is the minimum value, right? Which is the minimum value. Now, if you try to level, right, smooth out the sand, obviously you are going to get something which is between, right? You say, okay, this I'm going to get something which is not. So, okay, so here is okay. All right, so here I have this is the mean, and here I have this is the max, right? So this is the max. Now, if I level the sand pile, and obviously you are going to get something which is in the between, right? Level out. So something in the between. Okay, and this is something in the between and the value. All right, and then this is the sand. Okay, and this is the intermediate value, and we say, all right, so we can choose a point here. So this is the point C, right? So this is just the value of FC. This is just the value of FC. And because two sand, it's the same pile of sand, right? I just change the shape, right, from irregular one to a rectangle. The area does not change, right? Because the sand, I didn't add any sand and I didn't lose any sand, so area does not change, right? So the area of this, okay, so the area of this, which is integration from AB, fx, and dx. And the area of this will just be the height, right? So, okay, just the height FC and multiplied by B minus A. So the area of the two things, they shall be the same. And this exactly just gives me the FC times B minus A equals from A to B and Fx dx. And if you divide by B minus A on both sides, so you get AB and Fx dx. All right, so by this intuitive argument, it's very clear, right? It's very clear why this is true. If you want to look at the rigorous argument, you say, okay, what about the rigorous argument? So if you want to look at the rigorous argument, you quickly get, okay, if you want to do the rigorous argument, right? Okay, let me just quickly do it. You will see, let's say this is the max value, this is the minimum value of the function. You clearly have this Fx dx, right? It will be less equal to if I choose this one to be the max value, but if it will be no less than if I choose to be the mean value, right? Okay, so then I have this integral will be between the maximum value times B minus A will be between the minimum value of B minus A, right? And then what we can use? Okay, we use the intermediate value theorem. Intermediate value theorem says, okay, if you look at the max of F and look at the mean of F, you can always find something. So it's okay, so then you can always find there exists, right? So okay, so there exists a C between A and B, which you get something between, right? So you say, okay, so then I get AB Fx dx, this equals to C times B minus A. Because this one, right, from here, we know this one has to be equals some lambda times B minus A, and the lambda is intermediate. It has to be no greater than the max and no less than the mean. So this lambda is the intermediate value between the max and mean. And then by the intermediate value says this, okay, you see, it will provide, as we said before, you can always find C between A and B such that this lambda is given by the value of C, right? which is again from this geometric picture is clear. This is the max, this is the mean for any intermediate value, right? So this intermediate value you can always find the C such that it achieves that value. Okay, now let's look at the next example, which is a past AP question. It says we have a function g and it satisfies the derivative. Okay, we know the derivative of fx is given by this integration, right? And e to the negative t squared and dx. Okay, then we notice this is for x, right, between 0 and 2. This function, if you look at the function inside, right, so if you look at the function, this function is always positive. And then we say, okay, so derivative is, then we get, okay, the function, which is called integrand, right? So those things, by the way, so if you look at the fx dx, this x is called integrand. Okay, so the integrand is positive. Then of course we get the integration. The integral is also the integration is also positive, right? Okay, so then we get a function is strictly increasing. So first of all, we get a function strictly increasing. And then we want to also look at the concavity, right? Whether it's concave up or concave down. Then we know we need to look at the second derivative. But second derivative is just take a derivative again. Right? If you take the derivative of this, okay, look at the derivative of negative t squared dx. If you take the derivative by the part 2 of the fundamental theorem calculus, we know this is just e to the negative x squared, evaluated at x squared, right? Okay, and again, this one is also positive. Then we get the function is concave up. So from here, we get the function gx is concave up. Okay, so if you draw the graph will be look like this. It's strictly increasing and also is concave up. And this will be well, what looks like to be the graph. Okay. All right, now let's look at example 11. Here will function fx, which is piecewise defined. The function is discontinuous. From -1 to 0, so this is from -1 to 1, so it's x and y is 0. From -1 to 1, the function is -1, okay, so it's -1. And then from 0 to 1, the function is 1. Function is 1. Now we want to find the integration of the function when it's for x is from -1 to 1. Okay, for x from -1 to 1, we want to find this integration. Okay, start from here. Obviously, we have to look at different cases when x is here or x is here, right? They are different. All right, so first let's look at what happens when x is less equivalent to 0. X is less than 0, right? If x is less than 0, and then we get fx, but it's greater than -1, so it's -1x and fs ds, right? This will just be, so okay, from -1 to x, the function will be -1 ds. Okay, so if this is constant, it can move to the front. -1 times from -1 to x ds. Okay, so this is just -1 times x minus -1, so it's x minus -1. So you get negative x plus 1. When x is positive but less than 1, then fx, okay, so we can write as just two parts, right? This will be from -1 to x, fs and ds. Then we have to separate into two parts, from -1 to 0, right? Fs ds, right? So if you do the integration for here, you have to do both parts, right? To both parts, and then you plus from 0 to s, fs ds. Now within from -1 to 0, this is -1. When here, this one is 1, right? So then clearly you just get this -1 and the plus x. So we get this x. We get this x minus 1, right? Get x minus 1. Okay, then my function fx was my function fx. My function fx equals -x plus 1 when x is bigger than -1 but less equal to 0, right? And it will be x minus 1 if x is bigger than 0 and less or equivalent to 1. And this will be my fx. Okay, last one. Suppose fx is a continuous function on the closed interval AB. We want to look at, okay, what is the derivative of g prime x, right? What is the derivative of g prime x? Okay, here you see from the part 2 of fundamental calculus, we know if I look at the function fy, right? Fy, say this is from 0 to 1, no, from a to y, fs ds. I know this derivative with its y, this is just fy. Okay, so this is what we know from the fundamental theorem of calculus and part 2, right? Sometimes in different versions, they switch part 1 and part 2, but here let's say it's part 2. And then from here, we get the gx is just the f evaluated on x square, right? And now how you calculate the derivative? So okay, we can just use the chain rule. We can just use the chain rule calculus. This just equals the f, take a derivative, evaluate x squared, right, with y, and then times the derivative of x squared. Okay, so if you get that, you just get the f evaluated at x squared from here, and then times 2x. Okay, so what you get is 2x times fx squared. Apply the chain rule. Now, in general, okay, so okay, how about in general? We can do the same thing. In general, if I say define gx, you say, okay, from the integration from 0, here we say some hx and fs ds, then the gx will just equals to f composed with hx. We just use the chain rule. You get the g prime x is f prime evaluated on hx, and then, right, and then times the h prime x, and then you just get this f evaluated on hx, and because L prime y equals to fy, right? And then times h prime x. So this is just a general way to do it.